Okay, so let's start. Do you have any questions? All right. So from last time, we discussed several aspects, okay, of the Black-Scholes model. So first, the nature of the log return follows something like this. So here we won't distinguish, between the risk-neutral model or the usual model, because our interest here is to understand the effect of the bound motion and how to work with the bound motion. So from that point of view, we won't bother writing the tilde, okay, until we need to. So this is a log return. And let's clarify, okay, this is log return dynamics. Okay, from which, right, if you integrate both sides, okay, and using the fact, right, that if you add, right, the differential of any function in time, any process in time. So this is like adding the small changes, okay, from a time interval over a period of time. Then what you get is the net change, okay. Then so you'll be asked to explore this for different functions f, okay, in your homework. By the way, so this has a rigorous meaning and you should check it. But what this means, okay, this can be interpreted as a Riemann sum. Okay, as the limit as the number of division goes to infinity of the sum. Like this, okay. Where basically the idea is we have a time interval from 0 to t, and you start divide that into endpoints. T0, T1, T2, etc. Okay. Or rather, I think we call it from 1, so T1, T2, up to Tn. All right. Rather, this is Tn plus 1. But it doesn't matter. So the point is, right, the Riemann sum always divide the time interval into so many subintervals, and then you add the partial sum and see if the limit converge. Okay. The point is that when it's a simple expression like this, the limit always converges, and it converges to the net change. Okay. So that's very easy. But anyway, right, using this fact, which you asked to explore in your homework, we get that the log can be expressed like this, which basically just says the log price is this, because W0 is equal to 0. And then from this, you can solve for the model for the stock. Okay, so that's the Black-Scholes model for the stock price. So that's one aspect of it. Now, so several things that we need to look at, okay, several angles. From the probabilistic angle, we need to know how to compute this kind of expression. Okay. You know, not that this is out of the question, but something like this is also easy. So the reason is, all right, especially the first two expression, or, you know, I think for your homework, right, this kind of expression, because these are things that are intimately related to the stock model. So if you want to know how the stock behaves, okay, or how to price, you must be able to work out this expression. Okay. From the conditional expectation angle, you need to know how to compute, I guess, similar to the above expression, but now it becomes conditional expectation. For example, right, to give you a few ideas, maybe this as well. All right. So again, I guess the most relevant one in terms of pricing, it's this, because again, it's directly related, right, to the stock model. And when we do pricing at some other time point, conditional expectation, right, is what we use. These are, you know, again, mathematical exercises to ask you to, you know, apply the same concept to work with the prime motion, okay, to understand the structure of the independent increments, the prime motion. From the stochastic integration point of view, we want to explore the idea that WT is nowhere differentiable. The idea of an integral in terms of dWt, okay, stochastically in terms of calculus. And by the way, right, and then from the probabilistic point of view, this guy as a random variable, okay, meaning you fix a time and you look at this guy as a random variable, which, right, has expectation 0 and variance okay, and it can also be normal when WT is deterministic, sorry, delta T. Okay, here I use the notation delta, but it can be anything. Delta is just an integrand that represents the number of shares, for example, that we hold in our portfolio at any time. So stochastic integration, okay, is a rich subject. It has the calculus aspect, it has the, you know, probabilistic aspect, it even has a stochastic process aspect, where you look at this guy okay, so here I fix a big T, here I let the T runs, and this is called a stochastic process. More than that, is called a martingale. All right, and there are certain kind of properties of martingale that we want to that one can discuss. We don't do that in this class. Okay, I think this is a bit too complex to discuss. But anyway, so the one thing I want to bring out is actually one thing only about the martingale is that there's a statement that generically says something like this, that betting that there's no bounded winning strategy for betting against a martingale. Okay, so I'll talk about that just a little bit, and you're also asked to explore that in the homework. Basically, the Brown motion itself is a martingale as a stochastic process. Integrating against a Brown motion again gives you a martingale, and that is the mathematical reason behind the fact that the statement that one cannot have a winning strategy for betting against a martingale. Or basically, in terms of finance, what we're saying is there's no arbitrage opportunity if you invest in the stock. Because if you look at what we developed last time, the stock, investing against the stock, your portfolio has two components. One is the deterministic return component, not deterministic. There's a DT component for return, and there's a DWT component for the shock from the market. That component is what I said you cannot control, or an investor cannot control. There's no way one can select a portfolio that guarantees that to be positive, for example. So from that point of view, okay, there's no winning strategy for investing in the stock model. That's driven by Brown motion, which again, I guess, capture the market efficiency aspect, okay, of the model. So anyway, so there are many right angles that we want to hit before we even discuss pricing. Okay, after we cover all these grounds, then pricing becomes a straightforward exercise in terms of computation. So we'll revisit right these angles, not necessarily in any order in particular, but the goal is to build up right sufficient understanding in all of these aspects. All right, so that you understand how the Black-Scholes model operates, and then from there, okay, we'll discuss pricing. Any question? So let's kind of revisit the probabilistic angle a little bit. First, okay, namely these kind of computations. And so you already asked, I think, something like this on the homework to be turned in today. But again, right, it's worth mentioning that all computations kind of fall back on the normal distribution. Of WT, okay. So for example, I think I give you something like this. And I ask you to compute this, okay? Now, the interpretation of this is very straightforward. This is the probability that the stock expires in the money for a call option, that's all. Now, this expression by itself is not meant for you to take this whole thing as a single random variable. Yes, of course, but you're supposed to manipulate and work with this, right? So that you return every computation into a expression involving just normal distribution, right? Something like that, okay? And of course here, right, Z stands for the standard normal distribution, and here the calculation stops. because anyone can look up like the standard normal table to see what's going on. But right, I mean that the normal, right, the normality of the prime motion plays a crucial role, okay, in all this calculation. So you must be very fluent in the normal distribution, in particular, to work with the Black-Scholes model, all aspects of it. So another aspect, right, that I want to harp on again today is the computation of the moment general function of the normal, which, right, I claim to be the answer here is 1/2 t. So here, the general idea is the moment generating function of normal. Okay. So because, right, I will very quickly write down something like this. And all of these, again, come from the moment generating function of the normal. This is not something that you necessarily memorize coming from other courses. But again, in particular for this class, or anytime you plan to work with the Black-Scholes model, then not knowing the normal distribution, not knowing the moment generating function, it just puts you at a disadvantage. So the statement, the generic statement is if x is normal mu sigma squared, then expectation of e to tx, which is the moment generating function of x, is e to t mu plus 1/2 t squared sigma squared. Okay, so I want to kind of show the computation of this for a little bit because it reviews the structure of the normal, okay, distribution. First of all, one of the trick when you work with normal distribution is you never work with it as given. You always try to kind of do some scaling, try to do normalization. So for example, right, in proving this statement, you don't do this right off the bat. You try to do something like, let's say, suppose you have a standard normal. It's not the same. The reason is WT is a normal with mean 0 and variance t. That's why it's 1/2 t. Okay. Z is, and there's a t in front here. There's nothing in front of the W. Okay. So anyway, how would you go about showing something like this? Well, at the scratch level, like nothing is available to you, then what you have to do is to work at the density level where you integrate, okay, this expression with against the density of normal. Okay, like this. And to compute this expression, the technique, or rather it's just a trick, is completing the square. In other words, you see that, right, the two exponentials, their exponent add. So what you do is you consider this expression, okay, which becomes 1/2 z squared minus 2tz. And you see, this is almost a complete square if you add a t back to it. But if you add, you need to return. So this is the answer, which becomes 1/2 z minus t squared minus t squared over 2. So what we had, right, was the negative of that. So the top expression there, this expression, becomes e to the minus 1/2 z minus t squared plus t squared over 2 dz with 1/√2 pi. Okay. So maybe I forgot to mention that if you have a normal distribution, the density of such distribution will be this. Okay, for x on the whole real line. Again, not something that you may necessarily remember or memorize, right, from another class. I mean, everyone should have seen the normal distribution, right? If you have not seen the normal distribution, then you might be in the wrong class. But the point is that not even having seen the normal distribution, if you want to work, fluently in this kind of context, then memorizing something like this is not a bad idea. Like, and knowing how to work with it in this kind of context. Okay. So the reason is, if you look at this expression, you see that this this by itself is the density of a normal with mean t and variance 1. And the trick is integrating against a density will always give you 1. So that being said, the only thing that's left is this guy right here, which you can straightforwardly say is e to t squared over 2, which is exactly the proposed answer. Okay. Any question here? Okay. So we establish that this is e to t squared over 2. That surprisingly is enough for us to look at something like this, where x is normal mu sigma square. Why so? Because a normal mu sigma square is, in terms of distribution, is the same as a standard normal times sigma plus mu. Okay, this is called, right, a z transformation. So in other words, whenever you have a generic normal, you can always relate it back to a standard normal by a scaling and translation. So from that point of view, we can do this. Okay. Now, how does that work for us? Notice that the t mu, right, is a constant. Z is the only random variable here. So you got e to t mu, e to t sigma z. Well, t sigma is just a generic constant. We know what this is. So the answer here is e to t mu, e to the 1/2 t sigma square, or as people usually write it, e to t mu plus 1/2 t square sigma square. Okay. So how does that help us in general? Well, so you see, if you have a stock model that goes something like this, sorry, what am I saying? Sigma WT, right? Then taking expectation of the stock, right, will be expectation of S0 e to t mu plus sigma WT, which becomes, so it's up to you, right? You could take the point of view that this whole expression right here is a normal with mean t mu, so t, and variance sigma square t. All right. Remember that WT is a normal with mean 0 and variance t. So from that point of view, you can just apply this expression right here. Okay. So in other words, right, this is going to be S0 e to the mean is T mu, right? So it's like 1 times this, right? So it's going to be T mu plus 1/2, right? So the answer is 1/2 sigma squared T, but give me one moment. Yeah, that's correct because X is variance sigma squared. Yeah. So here, right, you look at it, the number that's multiplied in front is 1. Okay. So the multiply in front of the standard normal is 1. So this is your answer to take the expectation of a stock price. Any question on this? So again, right, that don't underestimate this kind of calculation because, for example, in the risk neutral model, when we got the stock price is S0 e to the R minus 1/2 sigma square times T plus sigma W tilde T, all right? So W tilde is just another kind of prime motion under the risk neutral framework. Then if we take expectation under the risk neutral probability measure of this, then it's going to be expectation of S0 e to the minus 1/2 sigma square T plus sigma WT. But, okay, but, so if you factor out this expression, then you got this is S0 e to the minus 1/2 sigma square T, and then E tilde of exponential of this. But this, right, this is nothing but 1/2 sigma square T. So it's going to be, which is S0. All right. So you do all this in between calculation to arrive at what we always expect that risk neutral expectation does, or is risk neutral probability does, right? That it evaluates the future stock price to be equal to the present stock price. Okay. But again, you see the road to go through this calculation is through the moment change function of a normal. Okay. Any question? Some more calculation, right? For example, suppose I want to calculate the probability, right? Or I think I did that before, the probability already. Let's say you want to do this, expectation of, let's say, W e to WT minus K plus. Okay. So I think you'll be asked to do this on this week's homework. But at least, so starting out, what's the first step? So the step, right, is you probably do not want to just jump in right away and start to work with the density of the prime motion, okay? You want to kind of pause a little bit and see what's going on. So what do we want to say here, right? That this, okay, is going to be 0 if e to WT, right, is less than K. And it's going to be e to WT minus K if WT is bigger than K. Okay. Second, right, there's something that you could do to help the calculation. For example, working with the prime motion is fine, but you see from this kind of idea of calculation, you don't start out with working right away with a normal in general. You try to revert back to standard normal if you can. Why so? Because at some point, if you don't know the expression, you will have to invoke the density. Okay? You do not want to work with a density of this form. It's much more complicated than a density of this form. Okay? This is the generic density of a normal. This is the density of a standard normal. When you do calculation, try to make your life as easy as you can. So here, right, WT is not that bad because WT is normal with mean 0 and variance t. But still, right, it's not standard normal. So what do you do to simplify this expression or to return it, right, to a standard normal? Well, remember the idea that, right, if x is normal mu sigma square, then x can be represented as sigma times z plus mu. So WT can be represented as square root of t times the standard normal. Okay. So in other words, this expression can be represented as expression of e to the square root of t, right, times the standard normal minus k plus, for example. Okay. Well, that's the best you can do here, right? That's the best you can do here. Then from this point on, you will need to start to do calculation. So what do you do? Well, you need to write that. So here, right? 1 second. So here, right, you need to write down the density of the standard normal. So that expectation will be, first of all, right, let's just do this. The integral from minus infinity to infinity of this function times the density of the normal. Okay. Now you observe this expression, and actually here, right, is where you do this kind of analysis. Maybe not with WT, right? But actually it's really WT too, but now it's in terms of Z. So you see that, right? E to the square root of TZ, right, minus K is going to be 0 when E to the square of TZ is less than K, or Z is less than natural log of K over square root of T. Okay. And it's going to be plus, right? And it's going to be e to the square root of tz minus k when the revert happens. Okay. So this is plus. So what that means is when you integrate this expression, there's the interval where it's 0 in terms of z. You ignore that. So in other words, the calculation becomes only from this value of this. Okay. Well, so the idea is, right, you get rid of the plus sign and make it into a linear function. Then the integral splits into two parts. That rather that's minus k, right? So, so first of all, right, how do you handle each of these expressions? The second expression right here, right, or rather this part, is just a probability, okay? A probability related to a standard normal. Why? Because this is the density of the standard normal. So this is just a probability, okay? So what that means is here, there's not much else you can do, but you can just write as a probability of the standard normal bigger than something, okay? Exactly that something is this expression. What to do here? What to do here is, again, you reinvoke, sorry, this is Z, right? I changed my Z, the same Z. Here, right? What you need to do here is to complete the square. In exactly the same style as we did for this expression, okay? You see, we did it for t here, right? But we did it for square root of t. Or we need to do it for square root of t, right? We need to do it for square root of t. And so you're like, okay, but we did the whole expression before, right? Why don't we just use that with square root of t? The answer is you don't have the integral from minus infinity to infinity, okay? Like we did before, right here. The limit now, right? The lower limit is no longer that, but it's gonna be the limit from this number. So after you complete the square, you will also get it to be a probability, but a probability of a second kind, okay, of another kind, of a shifted normal. So you need to normalize it. So the final answer will be something like this. So final answer will have a form of something n we call d plus, and then something n d minus, where that by definition n of x is the cumulative distribution of a standard normal. Okay, like that. So you're asked to fill in the details, okay, of this calculation in the homework of this week. So I'll stop here. But I just want to kind of guide you and show you, okay, the generic idea of doing this kind of calculation. Now, this kind of calculation, okay, is very, very relevant because it's going to be the basis of the Black-Scholes formula, okay, that we'll be discussing later on. So the Black-Scholes formula, which you might have heard before, is exactly the pricing formula for the call option when the underlying model is a Black-Scholes model we're discussing. So to understand how the Black-Scholes model, that Black-Scholes formula work out the way it does, this is a simplified version of that, okay? Simplified, okay? Because we don't use a stock model here. But once you can get through this, then the Black-Scholes formula almost is immediate coming from this. All right. Any question? All right. So that finishes what I want to say about the first aspect of things, right? The probabilistic angle. The conditional expectation angle, right? I talked about it last time. Let's review it real quick, okay? The conditional expectation angle the key technique there, okay? The key trick is to always express the future value as the present plus the future increment. Okay. The reason is, right, the future increment is always independent of the present value. Okay. Now, what do I want to say here? So it's almost like, the previous calculation, all these things we do, play on the stationary distribution of WT or play on the normal distribution. When it comes to conditional expectation, the emphasis now is on the independent increment aspect of the Brownian motion. So, for example, right, again, if you want to do something like this, okay, always assuming S is less than T, then this is again, remembering that the Brownian motion is known at time S. Anything involving that guy is a constant, so you factor it out. And do not factor out too much because this increment must stay together. This guy right here is what allows you to reduce conditional expectation into expectation. Okay. And then from here, you recognize that then here, right, from here on, the calculation is just using routine normal calculation. So like that. Okay. Any question here? All right. So next, let's go to the calculus aspect. Okay, the calculus aspect of the Brownian motion. Okay. So first, right, we want to understand this object. And as I mentioned, right, is the limit in some specific sense, okay, of the Riemann sum. Okay. So basically, again, the idea is at time ti, you multiply with the change in the Brownian motion, multiply with the change in the Brownian motion during the next time period. So, sorry, limit, right? Okay, that's fine. I just said the limit already. So the time interval right, again, is divided into n subintervals, etc. Right? So this is I equals. And so at each time point, imagine that this is the number of shares you hold at that time moment. So from this moment until the next moment, right, this is your net gain and loss from your investment because this is the stock change, for example, right? Okay. So it has to be in some specific sense because if you just take this in the regular sense, that is, just add all these terms up, they won't converge. So this does not converge in the regular calculus, okay, sense, because okay, well, because the Brownian motion is nowhere differentiable. Okay. So for that, let me just give you some example to explore this idea. So first of all, let's try this example, which everyone knows, right? What is the integral from 0 to t of t dt? Well, the integral from 0 to t of t dt would clearly be t squared over 2, right? Sorry, big T, right? Like that, okay? Okay, now, okay, you say that's easy. What is the integral, let's say, of t of, let's say, I don't know, d of t squared? Okay. Now you're like, what is this? Okay. You haven't seen that before, right? In calculus. Well, in fact, actually you did. You did see something like this. Okay, let me remind you. You've seen something like this. Let's say the integral, let's say t, okay? Let's say e to the minus t squared over 2 dt. Okay. So how would you calculate something like this? Now, if you look at this and you know your calculus, you see that's a very easy calculation because you will not hesitate to say, let u be t squared. Then du, right, is 2t dt, right? And you would replace this integral with 0 to square root of t, right? And then e to minus u over 2, right? 1/2 du equals blah, blah, blah. Now, but notice, right, what are you saying here? If u is t squared, right, look at this. So first of all, right, I want to see that you acknowledge, right, that this is the standard u sub that you get taught in Calc 1, right, or Calc 2, I think it's Calc 1. And you just do this, right, without thinking about it. But if you stare at this expression for a little bit, you see that actually you're saying something like dt squared is 2t dt. Why? Because you say that this is t squared. And so actually, right, this is not that strange. Or some people will say, yeah, that's obvious, okay? Or, right, this will be exactly what you usually see. You see d over dt of t squared is 2t. Or, right, you write t squared prime is 2t, okay? So you see that every one of these are just saying the same thing, okay? Every one of these are just saying the same thing. But one thing is, when you look at this expression, you only look at from a symbolic angle, meaning you play with like Lego pieces, right? You push this, you replace that, you make sure things fit, and then you integrate. Here we want to be a little bit more conceptual and understand what's going on. So again, right, conceptually, again, this kind of picture. At any time, we're saying that you're holding t shares of whatever that is, and you multiply with the change. So the underlying price is something like a t square process. Who knows why, right? But so your stock is like a t square process, okay? So your stock is a t square process. At any time, you hold t shares and you look at the change in the stock price and you multiply that, okay? Of course, you're gonna make a lot of money here because your stock always goes up, but that's irrelevant. We'll just try to understand what we're doing here. But so it makes sense, and the answer is what I say is this is nothing but so dt squared is nothing but t 2t dt, and then you can do it. Okay, like that. So in general, if you have a function is differentiable, okay, then when you integrate, let's say a function against this, okay, so what are we saying? Again, right, look at this. You can interpret this as number of shares you hold at time t. This is G represents your stock price movement. So this simply kind of symbolically, but this can be interpreted rigorously, is this. So you could, if you want, interpret as you multiply and divide by dt. But this is nothing but what we call G prime. And that plays exactly into the assumption that this is differentiable. So that's what we're writing here. Okay. Now, you see that, okay, exactly when because again, right, remember the financial interpretation we would like to do here is this is the stock price, right? This is the investment. You hold this many shares, the stock change, your fortune change. But exactly, right, in real life, you know, stock is not smooth at all. Any stock chart, right? It does this. That's why it's fun, right? You never know how it's going to move in the next time period. So exactly, you don't even need to know the calculus to see that this is troublesome. If you want to apply the stock price movement into this concept, because this is not going to be a nicely behaved piece, okay, of process. So in that sense, right, exactly because, right, the Brownian motion is nowhere differentiable, this sum will not converge, because if it were to converge, it will converge to something like this, the derivative. Okay. So in other words, what we're saying is this. If the Brownian motion were nicely behaving, then this would be something like this. Right, and I'll just do a W dot, okay, which is like the derivative of W with respect to time, which won't happen, which won't happen. Okay, so that's why you need a specific interpretation of this. Okay, so that's the essence of separating this object for an object like this dt. Okay, now okay, any question here? So maybe then you would ask, right, why is WT, right, nowhere differentiable? Okay, so remember, again, there's a lot of like deep things going on here, and I'm not asking you to go to the depth of everything like this, but try to appreciate the surprising or the you know, kind of the unexpected nature of this. Because when we say something is Brownian motion, what do we say? Right? WT is a Brownian motion if it starts at 0 has stationary increments, that is a normal distribution and has independent increments. Okay. So notice that all these statements are kind of like, I don't know how to say this, very local. Okay. They just describe how the WT moves locally. So it moves like a normal distribution. What it says is this, okay? And notice it doesn't give you any like a clear path. It says that by motion start at 0. On next step, right? How do you move? It doesn't say that, but it says, well, sample from a normal, and then move according to that normal value. Then at the next point, how do you move? It says, well, again, sample from another independent normal, and however that does. Okay. Notice, right, what I'm describing is very much like a binomial tree walk. And that's exactly that too, okay? The random walk. The Brownian motion is the continuous model of something called random walk. Anyway, right, point being is that from that description, it's hard to see where the nowhere differential comes from, okay? So I want to kind of give some intuition on why, right? That even from this description that we give, there is some clue that something is not quite smooth with the Brownian motion, okay? So it's like this. It's like this, okay? Uh, let me introduce this, which we'll use later on. So the answer, okay, or the clue, the partial answer, the partial clue comes from something called the quadratic variation process. Okay, of the Brownian motion. Okay. So what is a quadratic variation process? So roughly speaking, okay, if you have a function f, okay, as a function of time, the quadratic variation of f at time t, let's say denote like this, will be the integral of the differential of ft squared, if it exists. Okay. So, okay, what is this crazy object? It's actually not bad. What's happening is this, okay? That again, right? What are we looking at here when we say dft? Dft is a small change in the function, okay, as time change. So remember, right, when we do this, this is nothing but the net change from time 0 to t. So we want to repeat the same, but instead of adding just the change, we add in the change square. Okay. So to give you a clue of what's going on, all right. For example, let's just look at this, 0.1 versus 0.1 square, right? Which one is smaller? Well, I hope it's clear, right? That 0.1 is bigger than 0.1 squared. The point is that when a number is small, right? By small, we mean smaller than 1. By squaring it, you make it even smaller, okay? So what happens is when a differential, right, means a small change, by squaring it, you just make it even smaller and then add it up. So what's going on there? what I'm trying to say is this. If, okay, a function f is differentiable, then the quadratic variation of f will be 0. Okay, because basically its change is so smooth, so small, that when you square it and add it up, you get nothing. That's a surprising thing. Okay, basically, of course, right, there's a limit going on here, and so the limit gets smaller and smaller as you push time to 0. All right, so now, okay, you might be surprised, I hope, at this, because how can you add things square and you get 0, right? Well, it's not surprising, again, because of limit going on. So let me give you an example, okay? Let's say that f of t, right? Let's just say it's t. So in other words, I claim that this is 0. This is the simplest thing possible, okay? Then, well, why is this true? Notice that at any time you work with this and you want to get down to the the nitty-gritty part of it to understand what's going on behind the hood, under the hood, then you have to work things up at the Riemann sum level. Okay, like we can do things at the macro level for a while, but when the formulas do not apply anymore, then you have to go down to the definition and see what's going on. But here it's quite simple. What happens is, let's say we divide the integral from 0 to, right, oops, t. Let's say you divide into n subintervals of equal length. Okay, so each has length t over n. Okay, so what am I saying? I'm saying that delta t is t over n. So this is nothing but the sum, right, of delta t squared, I from 1 to n. Well, first of all, right, all the delta t are the same. They're all the same length. So this will be n times delta t squared, right? But what is delta t squared? Delta t squared is t over n. And you see exactly what's going on. Because then if you take the limit as this guy goes to infinity, you get exactly 0. Okay. So you just push things, right, as it goes to 0, you just push it smaller and smaller. So that if something is nicely behaved, smoothly behaved, if you square it, right, it disappears. Okay, it disappears in terms of the sum. Okay, what does that have to do with anything? So this quadratic variation concept applies to a Brownian motion too, because Brownian motion is a function of time. So the quadratic variation of the Brownian motion at time t is t, is not 0. Okay, so that's a clue to show you that the quadratic variation, okay, of the Brownian motion, sorry, that the Brownian motion, right, is not differentiable. Okay. Now, how would one go about showing this? It's quite easy. Well, again, right, follow the same concept. Divide the interval from 0 to t into equal length, and then add these guys. Well, but if you add these guys up, what are we having? We got WTI plus 1 minus WTI squared. Okay. All right. And you're like, okay, I don't know what this guy is. You do, okay? Because remember, Brownian motion, right, has independent and stationary increments of this form. So in other words, this is a, so without the square, okay, it's a normal with mean 0 and variance ti plus 1 minus ti, which is exactly normal with mean 0 and variance delta t, okay, because that's what we call delta t. So you see, when you square it, right, when you square it, this guy, right, expectation of WTI plus 1 minus WTI squared is exactly delta t. So here, let me remind you of something called law of large number, okay? Which says that if xi or iid with mean mu and variance sigma squared, then the sum of xi 1 over n converges to mu as n goes to infinity. Okay, so the long-term average, all right, of the IID sequence converges to its true mean. The Brownian motion has independent increments. What I mean is, right, this is WT, let's say WT3, W3, WT2, WT1, right? So the increment from here to here is independent of increment from here to here, all right? So this is actually summing a bunch of independent random variables. I don't need to divide by n because you see the delta t scales like 1 over n, right? Delta t scales from 1 over n. So actually, this is a version of law of large number, which say that this is just a sum delta t, which is by definition t. So when you add, right, the quadratic variation of the Brownian motion, because the variance, right, is delta t, right? The variance scales with time. That's why when you sum them up, they don't disappear. If you look at something like this, the variance, if you will, scale with time square. And that's why, right, the square here helps with the sum, and that's why it goes to 0. Okay, and that's why dt itself is smooth. Okay, why dwt itself is not. Or if you want, what it says is that at each time the change in the component change of each of the terms of our motion is quite big, actually. It has quite a large jump, if you will, right? During a time like this, you can expect that the change of the Brownian motion is of that size. Again, this might not mean much to you, but do remember, right? When a number is small, let's say 0.01, right? Its square root is much bigger than it. So when you have a small number, you take the square root, actually it goes bigger. So the Brownian motion is rough because of that. Its change is not on the scale of delta t, it's on the scale of square root delta t, okay? So all in all, right, as you see, we use this a lot. We say something like this: dt squared is equal to 0. dwt squared is equal to dt. Okay, we'll use this in the Ito formula to be discussed. Any question here? All right. So finally, right, I want to go back to um, the, one second here, where was it? So we talked about this a little bit, okay, last time. We will talk more about in details next time. For the last 10 minutes, I want to talk about the aspect of the integral as a martingale, okay? The stochastic integral as a martingale, or what's the idea behind betting against a martingale? Because you asked to explore just one very easy aspect of it in this homework of this week. So first of all, right, um, WT as a martingale. Okay. So first of all, what's a martingale? So a martingale is a stochastic process whose conditional expectation, right, is itself. In other words, it represents a fair price process. So what do we mean here? So actually, we have looked at martingale all the time. I just don't call it like that. So what we say is this, okay? XT. And then you have something like this. This is information, okay, available at time t. So if you for a time s before time t, if you look at the future value based on the current information, and you say that, well, it will be exactly the current value. If it works for any t and s, then this is a martingale. This, okay. I mean, to be technical, is x and information. So this is not strange. An example that we have looked at is in the binomial model, or actually any risk neutral stock price model. The discounted stock price is a martingale. Discounted. Okay, of course, under the risk neutral probability. Let me say it's a risk neutral. Okay. Why? Because the very definition of risk neutral says that if you take, right, for any, let's say t less than u, the discounted, right, stock price from u to t, right, must be equals to the stock price at time t, right? We argue that we call this the no arbitrage principle. We say that any point who viewed, right, the stock price, the stock value in the future, and discounted back to the present, must view that stock price as the same as the present price. But if you rearrange this expression, you see that is this. So exactly, this is what we call xt. This is xu, right? And this is information, so it doesn't matter. You can change that to the information. Okay, like that. Okay. Another one is the one we just introduced. Brownian motion is a martingale. Why? If for s is less than t, if you take conditional expectation of wt on ws, what do we get? Well, follow our same trick. Replace ws with wt with ws. Ws is a constant, so it comes out. And this is independent of ws, so it becomes expectation. But this is a normal with mean 0, so that's just ws. Okay. Now, why is martingale important? Because of this following martingale integration result, or the result is this. The stochastic integral against a martingale is a martingale. Okay. So what does that mean for our context? Remember, we say, right, last time that basically if you have a number of shares, a portfolio, right, where this represents the number of shares, portfolio, where this represents the number of shares you hold at time t, then this, right, represents the net gain and loss, right? Throughout the whole investment period. So remember the remark, right, that the discounted stock price is a martingale, or this is a martingale. So, okay, we didn't talk about it yet, but suppose that instead of looking at the net gain and loss, right, let's say that is you discounted. Okay. So, okay, we'll compare this and this later on. But trust me on saying that this and this are not that much different in terms of values. But what this says is this must be a martingale. Okay, this must be a martingale. Okay, what is special about a martingale, right? A martingale always has expectation equal to itself, right? Expectation equals to itself. So in other words, actually, here's the deal. If you have no information at all, meaning you start at time 0, right? If you have no information, then that's just expectation. But on the other hand, it's always the initial value because that's x0. So basically, a martingale always has constant expectation. Okay. Well, apply that to here. What does it say? Expectation of this will be equal, right? It doesn't matter what t is. It doesn't matter what this is, as long as it's bounded. Will be always equal to the value of this process as time 0. But what is this process? This is an integration from 0 to time t. So when t equal to 0, that means you have not started anything. So actually, this is equal to 0. Okay, because there's technical reason here, but financially you can understand that if you have a lot of money to buy a lot of stocks, unlimited, like infinite, then you can, make a swing in your favor, right? So you see, this is the rigorous result, and which again, we won't prove, we won't say anything. I'll just ask you to kind of trust that. But basically it says that when you look at your investment, but on the discounted sense, you gain nothing. Your expectation zero. Okay, so of course, right, you unravel this and you compare with this, which is the true net gain loss. You see that it allows you to gain something equal to risk-free rate. That's it. What you gain is equal to risk-free rate. As after we develop the Ito formula, we'll revisit this and I'll show you. Okay, but I I I, I just want to point out, right, that exactly, right, the martingale aspect tells you that there's no portfolio that can clearly win over the market. And you kind of saw that already with the replicating portfolio, okay? So you're asked to kind of do some numerical play with the Brine motion, in this week's homework to explore this aspect. But we will not say much about the martingale in this course, besides something like this, and maybe I'll go back and shed light on this after we develop more tools. All right. Any question? Okay. If not, then I'll see you next time. Thank you.